Grade 12, welcome to the Grade 12 Mathematics, and this is our session 2. We are still doing Euclidean geometry, and today I just want us to focus on equiangular triangles theorem. So it's equiangular triangles and similarity theorem. Okay, let's take a look at the content outline. Today we're going to be using this textbook, Mind the Gap Mathematics Study Guide, where we just extract some of the notes and some of the examples from there. Okay, it's session 2, and we're just going to focus on equiangular triangles and similarity. Okay, great stuff. Before going further and just start introducing you to equiangular triangles and its theorem, let us first look at some key basics, and this is some sort of a revision about similar polygons, right? So you already know what is a polygon. A polygon it's made up of line segments that are joining each other. 3 or more line segments that are joining each other, they can form a polygon. For example, triangle, rectangle, trapezium, and others. Those are polygons because they are made up of 3 or more line segments joining together, right? So what are similar polygons? Remember similarity that you did from grade 9 when you learned what it means when we say things are similar, triangles are similar, right? What do we mean when we say these two shapes are similar? So similarity means that they have the same shape but not necessarily the same size, right? So 2 things will be similar or 3 things will be similar if they have the same shape but they can have different size. Then they can be called similar. For example, every square is similar to every other square. Take a look at the first square, second square, and the third square, right? You can see that their lengths are different. This is the smallest. This one is quite big, and this one is the biggest, right? So you can see that their size are different, but all these squares are similar to each other. But what is the reason? Okay, we already learned from grade 9 that there are 2 conditions, only 2 conditions, right? And if you can prove one of them, then you can basically conclude that these things are similar, right? So if polygons are similar, or polygons will be similar when, number 1, very, very important, this is our number 1, when all pairs of corresponding angles are equal, right? And when that is the case, we say those 2 polygons are equiangular, coming from the word equal angles, right? So they just name it equiangular. So now if our polygons have all corresponding angles being the same, being equal, then we can say that they are what? They are similar. So that's the first condition. For example, look at the squares. We know that all squares have what? Have an angle of 90 degrees, right? There. All of them, they have 90 degrees, right? They have 90 degrees, 90 degrees, 90 degrees, and 90 degrees. So you can see that the corresponding angles, this angle here is corresponding with this one, which is corresponding to this one. So it's corresponding angles. They are equal. Even this angle is corresponding to this one, which is corresponding to this. They are equal, like this, like this, like that. So you can see that if corresponding angles are equal, then we can conclude that, okay, these polygons are equal. And we can actually say they are actually equiangular. We use now the term equiangular. Okay, so number 2, second condition, and this was also taught in grade 9. It's very, very important that we revise this because it's very, very important for you to understand equiangular triangle theorem. Okay, so number 2, if all the pairs of corresponding sides, right? In the first condition, we were talking about the angles, right? But however, if you can find that all the pairs of corresponding sides are in the same proportion. Remember proportionality that we did in session 1, where we talked about how you can check whether things are in the same proportion. Don't forget about proportion. We mean that their ratios must be the same. So if all the corresponding sides are in the same proportion, what does it mean? If all the corresponding sides, when you get their ratios, you find that their ratios are equal, then you can conclude that they are what? Those things or those polygons are similar. So that is similarity. Okay, so this is the symbol that is used for similarity. It's just those, okay, maybe if I can highlight it here, it's just those three lines that are like vertical like that. So it's used to show similarity, and we say this polygon is similar to this polygon like that. Okay, so okay, let's just take a look at an example for you to understand this second condition that says if all the pairs of corresponding sides are in the same proportion, then we can conclude that, okay, these polygons are similar. Okay, look at example 2 here, that is extracted from Mind the Gap Mathematics Study Guide. Okay, so you are given that you have a polygon EABED, right? So, and you also have this polygon PQRST, right? So consider it's a pentagon, by the way. So there is it. They say ABC, DE. Okay, so obviously here they wanted to write C, ABCDE, and you also have another pentagon PQRST, right? So if you find that the corresponding angles are equal, this angle is equal to this because that angle is corresponding to that, then this angle is corresponding to this, this angle is corresponding to this, then this angle is corresponding to this, and this angle is corresponding to this. So if you find that the corresponding angles are equal, you can conclude that the two pentagons, they are what? They are similar, right? Using the first condition. Or, however, number 2, this one, very, very important. If you find that all the pairs of corresponding sides are in the same proportion, that is, their ratios are the same, then you can conclude that they are what? They're equal. So this is how you can show that the corresponding sides are in the same proportion. So you can say AB is corresponding to what? To PQ. So you'll say AB over PQ as they've indicated here, right? So it's AB over PQ. If it is equal to BC, then over what? Over QR, because BC is corresponding to QR. Then that's another ratio, right? Another ratio, then we can say DC over what? Over SR. DC over SR, because they are corresponding. Then is another ratio, and another ratio is what? Is ED over what? It's corresponding to TS. And the last one, we have EA is corresponding to what? To TP. So if you find that all those ratios of the corresponding sides are in the same, are equal, then we can conclude that the sides are in the same proportion. Then you can conclude that the two pentagons are similar, same as we have triangles. For example, if I have triangle, this triangle and this triangle, and I have A, B, C, and I have D, E, F, and I calculate the ratios of the corresponding sides, and I get that AB over DE. So if it's AB over DE, it's the same as, if I get that, is the same as AC over DF. If it's the same as AC over DF, which is also the same as what? As BC over what? Over EF. Over EF. Then if I can manage to prove this, right, then I can conclude that triangle ABC is similar to triangle what? To triangle DEF. So that is what we mean, that if the corresponding sides are in the same proportion, then we can conclude that those two polygons are similar. Okay. Okay, let's now take a look at the theorem, right? And you know, from a theorem, You must know its statement and you must know how to prove it. And I just put everything here and I will explain. Okay, the theorem states if two triangles are equiangular, then the corresponding sides are in proportion and therefore the triangles are similar. Interesting theorem. Very, very interesting. Look at this. They are telling you that if you have two triangles and they are equiangular, what do we mean when we say triangles are equiangular? We mean that their angles are equal, right? Then it means that then the theorem is suggesting that then also you are going to find that their corresponding sides, right? Their corresponding sides will be in proportion, right? It means that when you calculate the ratios of their corresponding sides, it must be the same, right? Then that's what the theorem is suggesting to us. And it also says, therefore, the triangles are similar. Ash. So if you look at the previous slides, it's basically what we did there, right? So sort of like that key basic, it will really help you to conceptualize the theorem. It's very simple. If triangles are equiangular, if the angles inside the triangle are equal, right? If you have two triangles and you find that the angles there inside are equal, what will happen? It is saying then the corresponding sides, the sides that are corresponding, they will be in the same proportion. That is, their ratios will be equal, and therefore those two triangles will be similar. So that's what the theorem is stating, right? Okay, so what is our given information? Now I just want us to prove this theorem. So our given information, let's take a look at triangle ABC. It's this triangle here. Oh, maybe I can use a red color to just show this one. ABC. Okay, and let's also take a look at triangle what? A triangle DEF is this one above, right? DEF. Okay, what is your given information? You are given that triangles are equiangular. It means that the angles are equal. It means that this angle is equals to this angle is equals to this, and this angle is equal to this angle. So that is our given information, that angle A is equal to angle D, angle B is equal to angle E, and angle F is equal to angle C, obviously, angle C. Then we have to prove that what? So we are just given that triangles are equiangular. Then what is the theorem suggesting? Then the corresponding sides will be in the same proportion. So in other words, we have to prove that DE over AB is going to be equal to what? EF over BC, which is going to be equal to what? DF over what? Over AC. So this is what we have to prove now from this theorem. Okay, so if we want to prove this theorem now, we have to make a construction, and I already wrote for you there the construction that you have to make. You go, because you have if you check these two triangles, they don't have the same size, right? DEF is smaller and ABC is bigger, right? So you go on the bigger triangle, and on the line AB, as I've written there, on AB, mark point P, or you can choose to say mark point M, or any point or that you want, right? You're going to mark point P such that your AP now is gonna be equals to DE. So you are marking a point on that bigger triangle so that your AP will be equal to DE, right? So that's what we just wrote there. Okay, so, and also mark point Q on AC on this side also. AC, I'm gonna mark point Q such that AQ is equal to what? Is equals to DF. So basically in this theorem, they will give you two triangles that are not of the same size. You will go to the bigger triangle and you are marking those points. You can choose to name them M, you can choose to name them X or Y or something, those points. But so long as you don't use the letters that are already used in those triangles. So what we did, we go on this bigger triangle ABC, we are marking a point P such that AP is equals to DE, and we're marking a point Q such that AQ is equals to DF, right? After that, we're gonna draw PQ. So we're gonna join P to Q, right? I'm just gonna join it using dotted lines. So after that, you join P to Q, right? So now you can start proving. So that was a construction. Okay, so now to prove, what you do, you are going on these two triangles now that you just, the one that you just formed and the one that was the smaller one there above. Okay, so we are going to say in triangle APQ, you can see it's that triangle that we just formed, and in triangle DEF, the one above, right? In triangle DEF. So what you do, you go and prove congruency. So you know that in congruency, you just need to find three things that are equal between the two triangles, then you conclude they are congruent. So don't forget, to say things are congruent, we mean they have the same shape and same size. Hence, we just constructed to make those triangles to have all those. Okay, so we're gonna say AP, as you can see, as our first thing for congruency. AP is equals to DE by construction. We just made it by construction, right? Hence our reason will be by construction. And we can see that angle A, this is number 2, right? To say angle A is equals to angle D. And this was a given information because they told us that the two triangles were equiangular. It means that this angle is equal to that one. So it's a given information. And number 3, our last thing to identify is that we can see that AQ is equals to DF by construction also. We just made AQ to be equals to DF by construction. Therefore, after getting all those three things, we can conclude that therefore these two triangles are congruent, and the symbol for congruent is this one that they've just used here to say now, because we got three things that are equal between the two triangles, therefore we can conclude that triangle APQ is congruent, right, to triangle what? DEF. By what? We got the side and an included angle, and the side being equal, side, angle, side. So don't forget how to prove congruency from grade 9 there. Okay, after proving congruency, we can conclude something, right? Immediately once you identify three things that are equal between the triangles using those approaches of congruency to say side angle side, or you can get side side side, or something like that. We can deduce something, right, from congruency. We know that if we prove that things are congruent, it means that they have the same shape and they have the same size. So after proving congruency, we can now conclude now to say angle E, or we can say angle P1, and let me just use a green color. Angle P1, therefore angle P1 is equals to angle E, right? Angle P1 is equals to angle E, because the two triangles we have proven that they are congruent. It means all their sides will be equal and all their corresponding angles will now be equal because they are congruent. So we can deduce that angle P1 is equals to what? Angle E, and this is from congruency. So we can write from congruency, and it's coming from congruency. And also we can also deduce that, but we know that at the first place our angle E was equals to what? Was equals to angle B, right? Do you remember? So now we are deducing that angle P1 is equals to angle E. But this angle E, initially it was equals to angle what? Angle B, right? So now we can conclude that it means that angle P1 will be equals to what? Will be the same also as angle B, because both of them are equals to angle E. So I don't like this reason that they give here. Let me just delete it and write this one so that you can really understand it much better. Okay, so we are saying that angle P1 now will be equals to angle B, because both of these angles are equals to angle E. Both of them, they are equals to angle E. Then they are also equal. So after doing that, look at something here. And I want you to see this. I don't know if I can use a yellow color. Look at this. I have something like this now. This angle is equal to this angle. What can you see? Corresponding angles are equal. Therefore, we can now deduce that PQ is going to be parallel to what? To BC. PQ is now parallel to BC because what? Corresponding angles are being equal. P1 is equals to B, right? So it means that because corresponding angles are equal, we can deduce that this line is parallel to what? To this line. So after deducing that that line is parallel to that line, what can you do now, right? So look at this. It means that we are now thinking of a certain theorem that we did in session 1, proportionality theorem, to say if a line is drawn parallel to one side of a triangle, it will divide the other two sides in the same proportion. So we can now deduce that AP, right? AP over AB. Why are we choosing AB? Because we know that there is AB in that thing that we want to prove there, right? So therefore, that's why we are saying we will use this corollary to say AP over AB. That's why we are choosing AB instead of PB, because PB won't help us because it's not in something we had to prove there, right? So we are going to say AP over AB is equals to what? AQ over AC over AC. Why are we saying those things are in the same proportion? Because of proportionality theorem, and we can see that PQ is parallel to what? To BC. I really don't like these reasons that they are giving here. Let me just quickly delete them, and let's write the reasons that we taught. Okay, so it is because of proportionality theorem, right? It is because of proportionality theorem, and because we had proven that PQ is parallel to what? To BC. That's it. So it's because of proportionality theorem. Then we can conclude that AP over AB is equals to AQ over AC. But look at this. Very, very important. But let me highlight this in green. But initially by construction we said our AP is equals to what? Is equals to DE, right? AP is equals to DE. And also by construction we said our AQ is equals to what? Is equals to DF. It means that we can go and replace and substitute. Where there is AP we can put DE. Where there is what? Where there is DF we can now put, where there is AQ we can now put what? We can now put DF, right? So that's what they just did there. They replaced AP by DE and AQ by DF. And now they've proven this part of the theorem. Can you see? They've now proven that indeed DE over AB is equals to DF over AC. So in order to prove this third part of the theorem, so we can similarly do it by the same method. To say, similarly, we can prove that also DE over AB will be the same as EF over what? Over BC, right? Similarly, by following the same procedure, we can also prove that DE over AB will be the same as EF over BC. If we make the same construction of those angles, of those sides being equal like that, we can similarly prove that. Then we can conclude that indeed DE over AB is equals to EF over BC, which is equals to DF over AC, to really prove that indeed if the triangles are equiangular, then their corresponding sides will be in the same proportion. Then their corresponding sides will be in the same proportion. And therefore, we can now conclude that those two triangles are similar, right? Okay, let me just repeat this theorem because you might be maybe confused or saying, oh, this theorem has a lot of things to do, right? But it's very, very simple. Step number one, you just need to know how to construct. You'll be given two triangles, the bigger triangle and the smaller triangle. We said step number one, on the bigger triangle, what you do, you go and mark off the points, right? Such that those points, those lines will be equal to the lines of the smaller triangle. After that, you prove number one, congruency between the two triangles, right? After proving the congruency between the two triangles, what do? From congruency, you can deduce that indeed it means if this angle here is equal to this angle there, and this angle was initially equal to this, therefore we can conclude these two angles are equal. And if these two angles are equal, we can conclude that the two lines are parallel because corresponding angles are being equal there. After deducing that, you can just use proportionality theorem to show that, okay, now there's a line drawn parallel to one side of a triangle. I can now prove I can now get the ratios of the sides and equate them. Then you just go and replace by those you have done in congruency. Then you have proven the theorem. Very simple. Okay. Don't forget, you really need to understand and to know how to prove the theorem because it's examinable. If you take a look at past papers, you'll see they'll ask you to prove those kind of theorems. So you need to know, and it's basically free marks, and it's the marks that you know for sure. I already have them in Euclidean geometry. Okay, so I just want us to look at this one example and just conclude this lesson because really there's no much of the things that you really need to know. So most of the things you'll get them once you are practicing past papers, right? As soon as we are done with these sessions for Euclidean geometry, you must be starting getting past papers and working on them so that you may really conceptualize and really try to figure out a way and a method and that examiners use in this topic. Very, very simple. Okay, so let's look at this example. It says in the diagram, PQCB is a cyclic quadrilateral, right? So we are given that PQCB is a cyclic quad. What does it mean? It's a quadrilateral that its corners, its four corners are on the circle, right? So the chords BP and CQ are produced to meet A, right? such that AQ, okay, very important information, AQ is equals to BC. Okay, so they're saying AQ is equals to BC. Okay, so 1.1, they are saying prove that triangle APQ, let's highlight triangle APQ is this triangle, or maybe I can use a different color there. APQ is that triangle is similar to triangle ACB. ACB is that bigger triangle there. Sorry about this line. ACB. So it's that bigger triangle. Prove that the two triangles are similar. So if we want to prove similarity, we say we can prove similarity by two things. Don't forget, we said you can actually check the sides if they're in the same proportion, right? So if the sides are in the same proportion, then you can deduce, okay, these two triangles are similar. Or number two, you can check the angles, whether the angles are the same in between. So if the angles are equal, then you can conclude the triangles are similar. So in order to do this, you realize that you really need to know the theorems that you learn in grade 11, right? So if I just get time, maybe I'll revise on them, right? But you'll see it on this lesson that these grade 12 theorems that you learn, they really need that basic of the theorem that you learn in grade 11 and all that. But if we get time, I'll really definitely put the revision for that. Okay, so let's do this. So we want to prove similarity between the two triangles. What we do, you'll say in triangle APQ and triangle ACB, you are going to identify three things that are equal. So you can either check whether their ratios are the same of the corresponding sides, or the angles are the same. But because obviously in these two triangles you are not given the length of the sides, so we can't use that one for ratios of sides being in the same proportion. But obviously we're gonna go for angles because there's no other way, right? So angles. So if you find three angles are the same, then basically prove they are similar. Okay, so let's check APB is that smaller triangle, and ABC. There's an angle that is common. Look at angle A. It's found on both the smaller triangle and the bigger triangle, right? So very simple for that. Angle A is what? Is common, right? Can you see this? Angle A is common. Okay, number two. Let's take a look at another angle. Check angle Q2. Check angle Q2 here. Remember, this is a cyclic quad, and there's a theorem that you learned in grade 11 that an exterior angle of a cyclic quad is equals to the opposite interior angle. Do you still remember that theorem? Okay, so we can conclude that Q2 is equals to angle B by what? Exterior angle of cyclic quad, right? So we know that the exterior angle of a cyclic quad is equals to the opposite interior angle. And also this one, P2, is an exterior angle, right? Is equals to the opposite interior angle. But really, if you want to prove similarity with triangles and all that, what you can basically do, just get two angles that are equal between, right? When you go to the third angle, it is obvious that it's going to be equal. Obviously, if I have two triangles and I have two angles being equal between them, then obviously the third angle will be equal, right? So you don't really need to think a lot. You just need to get two. When you go to the third one, just identify that. It means this one will be equal to this by the reason that I will give you. So angle P2, we can conclude, is equals to angle C, right? You can just write, it's because it's the third angle of a triangle. So we know that obviously if two angles are equal in between, the third angle will be equal. So you just say third angle of a triangle. So therefore you can conclude that therefore triangle APQ is similar. This is the symbol for similar to triangle ACB by what? By angle, right? That is your reason. So you have proven similarity between the two. Okay. Number two. Hence, prove that AQ squared is equals to AB times PQ. So in most cases, you realize this immediately when you start treating past papers. Most of the past papers, when you start working on them, you realize that if they ask you to prove similarity, they would want you to use that answer that you have proven. For example, if you prove that this triangle is similar to this triangle, then they would actually give you some of the following questions that are corresponding to that question, that first question, right? Just like this question, they are saying hence. Every time they write the word hence, they are basically saying the answer that you get above should help you to get the answer in this question. That's it, right? It means that you should be helped by 1.1 to get the answer. That's why they are saying hence prove that AQ squared is equals to AB times PQ. How do you do this? How will the answer above help us? Remember, in 1.1, we have proven that triangle APQ is similar to triangle ACB, right? APQ is similar to triangle ACB. So, from this, remember, from similarity according to equiangular triangles, if triangles are similar, it means that their corresponding sides are also in the same proportion. So from similarity, we can move to proportionality. So from similarity, we move to proportionality. If things are similar, then their sides are in the same proportion. How do we move from similarity to proportion? We have this statement. These two triangles are similar. We can move to proportionality. How do we do it? We are going to say AP over AC in that same way is equals to BQ. It's not B, it's PQ. Sorry about that. It's PQ over what? It will be over CB. Then this will also be equals to AQ over what? AB over AB. So this is because the two triangles are what? Were similar. So you can write triangle because triangle, let me just write it, because triangle ABQ was similar to triangle ACB, right? So that's it. From similarity, you move to proportionality. And how do you do it? You use the letters, the AP over AC. Then you will say is equals to APQ over CB, which is equals to AQ over AB, like that. Okay, so now it's gonna be easy for you to prove this thing that they want you to prove, right? You just need to check which sides are needed in the statement that I have to prove. There is AQ, right? Let's check our AQ is there, right? Is there any other AQ there? There's no any other AQ, right? Let's check another thing. We have AB, right? AB is there. We also have what? We also have PQ. Can you see on the statement that we have to prove here? We also have PQ. So I just highlighted the things that are needed to be proven. So really this one won't, or let me just write it so that I will just cancel it so that you will understand why we won't need it. You see, for us to prove, you realize that this one is useless, right? It's not useful in what we have to prove because we have all those kind of things. So we're just gonna write this one, and it's coming from similarity. So it's our first step to say PQ over CB is equals to AQ over AB, right? Because triangle APQ was proven to be similar to triangle ACB. So we are just basically saying from similarity we have moved to what? To congruence. To proportionality. Sorry. From similarity we have moved to proportionality. Now we have to solve for AQ, right? Remember, we have to solve for AQ. So we're gonna cross multiply, then we'll have our AQ. It's multiplying with what? With CB. It will be equals to what? It will be equals to AB, which is multiplying with what? With PQ, right? So after that, remember we want to prove that AQ squared is equals to AB times PQ. This side is already perfect. It's fine, right? So let's go on our given information. Don't forget, we were given that AQ is equals to BC, right? So we have that, but AQ is equals to BC. So it means that where there is BC, we can substitute by what? By AQ. Very simple. So where there is BC, I'm just going to substitute by AQ. Then let's see how we can prove like that, right? AQ times AQ, it will be AQ squared is equals to AB times, why am I saying BQ? It's PQ times PQ. So you have proven that thing. So, but what's really most important here, you must know how to move from similarity to proportionality. And also, if they say prove whatever, you must be able to identify the sides that are needed to be proven and take a specific proportionality there. Then you just cross multiply and try to prove that looking at the given information and all that. Okay, great stuff. I hope you enjoyed the session. We were doing session 2, focusing on equiangular triangles theorem and similarity. Okay, so what I can encourage you after this session, just go and look for past papers, or if you need them, you can just comment on this video here on YouTube and just say, can you please send me past papers? I'll just drop my WhatsApp number. Then you can just text me from there, and I can send you papers that you can start working on in order to conceptualize this content. Okay, otherwise, thank you very much for joining, and just wait for the next session. We are also having session 3, where we'll be focusing on I think it's proportionality triangles going to similarity like that. Okay, otherwise, thank you very much for watching. Enjoy the rest of your day, and goodbye.